So in this chapter, we're going to talk about measurements, something that you already did in the lab, and something that some of you may have easier time dealing with, especially if you grew up with the metric system. Okay? So scientists use metric system instead of imperial system because it makes sense, unlike the imperial one. One of the versions of the metric system, called the International System of Units, okay, it is pretty much a standard that is used in chemistry. Now, what it means is that we have a lot of different metric system units. International system, or SI, because the original language of measurements was French. Okay, so Système International, I suppose. They use very specific units for length, volume, mass, temperature, and time. So on the right column, you see the international system units. Okay? Cubic meter, meter, so length, volume, length, mass, temperature, and time. Now, we can use it in the regular life, totally. But if you want to talk about the density in chemistry, you usually deal with relatively small amounts. You deal with grams and milliliters and cubic centimeters. Am I making sense? So you can totally express the density of iron as 7,600 kilograms per cubic meter, but that's going to be a bit of a pain to translate it into grams and cubic centimeters. This is why in chemistry we use grams, liters, cubic centimeters, or centimeters cubed. I promise I will bring a better pen next time. Celsius instead of Kelvin. One of the reasons, so now outside it's about 21 degrees Celsius. Okay? Reasonable, right? Water freezes at 0, boils at 100. You can kind of see the references. I will tell you that it's 294.15 Kelvin outside. That's a bit of a stretch. This is why we use Kelvin for science, not for daily life. So let's start with the volume. So the volume is the space that substance occupies. Obviously, you'll know it. So in international system, we use cubic meters. I want to emphasize what a cubic meter is. So imagine that this is a cube. It's a cube, right? And each edge is 1 meter. Right? How do we find the volume in this case? Height by width by length, right? Make sense? So we do 1 meter multiplied by 1 meter multiplied by 1 meter. What do we get? 1 meter cubed. All good? That's the idea. This is why we call it cubic meter. How big is a cubic meter? I'm going to use imperial units to give an idea. It's about 250 gallons, more than that. That's a lot. Like, that's a lot of gallons, So for the lab, it's not a useful unit. So in the lab, we're going to be using liters. That's by chemical measurements That's a pretty large unit, but mostly we use milliliters. Okay? Well, good? So we're going to talk about the prefixes, but just a reminder that milli is 1,000th part. So just first encounter here, 1 liter is the same as 1,000 milliliters. Okay? Okay, so I was raised in the environment with a metric system. Imperial system still makes no sense to me. I'm kind of used to it, but it makes no sense. So, for your daily life, sure, that can be useful, or that can be useful. 1 quart is equivalent to 946 milliliters. And we will get into conversion factors and all that conversation later. But this is right now what I would suggest you focus on. That great property of metric system units to come in the fractions or factors of 10, 100,000, 10,000, whatever. So, length. Meters. How big is a meter? A little bit more than 1 yard. It kind of gives you an idea, right? Like my height is about 1 meter 78 centimeters, or 1.78 meters. Okay, so you can kind of measure it up. In chemistry, well, we don't use length too much, but if we do, it's centimeters, not meters, because we're not dealing with the huge device. Unless it's industrial, that's a different story. Okay? Sounds good? So, useful relationships. 1 meter is equivalent to 100 centimeters. I'm going to add one more. 1 meter is equivalent to 1,000 millimeters. And 1 centimeter is equivalent to 10 millimeters. Okay? Now, these are relationships between the inches, the yards, feet. Now, this relationship is basically a standard, because in many areas of human endeavor, traditionally we used inches instead of metric systems. So, for example, if you look at the calibers of guns, practically all of them are measured in inches. For instance, the main caliber on American battleships, which are now retired, is 16 inches. So, scientists, people agreed upon the fact that 1 inch is exactly 2.54 centimeters. It's not measured, it's just an agreement. Okay? Sounds good? Mass. In international system, it's kilogram. Okay? 2.2 pounds. Right? In chemistry, we do not operate with kilograms. We work with grams. Useful relationship here is this. Moreover, if you work with little, super tiny quantities, you may need to work with milligrams. Remember, milli is 1,000th part. So I'm just going to add that 1 gram is equivalent to 1,000 milligrams. Okay? Good? Awesome. Temperature. I'm going to go on the round. I would love to talk to Mr. Fahrenheit. and ask him what he had in mind when he decided that 32 Fahrenheit is the temperature of water freezing. Why not 33? And why is the range from freezing to boiling has got to be 180 degrees Fahrenheit? So honestly, for me, this makes no sense. But to be fair, I grew up with Celsius, so I might be biased. In Celsius, the temperature of water freezing, the temperature of water freezing is 0, and water boils at 100. Okay? All good? Now, this is boring and pedantic, and I know that. But we have to get through this. When you look at Fahrenheit scale or at Celsius scale, when you write down the temperature, for instance, you write down 28 degrees Celsius, you write this little degree sign, right? When you write down the same temperature in Fahrenheit, you also use the degree sign. Do you follow my train of thought so far? But if you want to write down the same temperature in Kelvin, you do not use the sign of a degree, and you do not say the word degree. So you can say it's 28 degrees Celsius, or 82 degrees Fahrenheit, or 301 Kelvin. Making sense? Now, fundamentally, what is the difference between the Celsius and the Kelvin scale? The degree, the step, is the same. Let me explain what I mean. So imagine that this is 0 Celsius, okay? Which is equivalent to 273 Kelvin. Are you with me? Do you follow? Let's say this line here represents 5 degrees Celsius. So we did 5 steps up. Do you follow? Right? 1, 2, 3, 4, 5. Okay? All good? In Kelvin, we use the same 5 steps. So it's going to be 278 Kelvin. So one step on the temperature scale, whether it is Celsius or Kelvin, the step is the same. We start at a different point. Making sense? Okay. Fahrenheit is all screwed up. We're going to get to the conversion. Time. Seconds and, you can use minutes, you can use hours. I just want to come back to the, why do we need 2 systems for temperature? Why do we need Celsius and why do we need Kelvin? The Celsius system appeared first. Okay? And then, during the boom of physics in the late 19th century, Lord Kelvin, British scientist, demonstrated that there is the lowest possible temperature, which is 0 Kelvin. Nothing, not a single object in the entire universe can have lower temperature. There are no negative temperatures in Kelvin. Does that make sense? In Celsius, it is 273 degrees with a minus sign. Okay? When we are going to do those calculations actually. When you do scientific calculations, when you use physical laws, chemical laws that require temperature, If it's an absolute temperature, it must be in Kelvin. Temperature in Celsius will result in a mistake in the error. Okay? So, okay. Some of the examples are outright stupid. Length, mass, or volume. Mass. Like, the question has an answer. Meters, what do they measure? Okay. Grams, what do they measure? Liters, what do they measure? Okay, SI unit, SI, not metric, but SI unit for the volume. Remember, SI have big S units. Volume, meter cubed. Specifically for SI. Mass, kilos. Length, if the volume is cubic meter, the length is just meter. And temperature, Kelvin. Okay? Any questions so far? So this is where, you know, I teach this is my, what, 4th time teaching this course. And the funny part is that we have a lab on Monday. And you have like a learn on the fly, all that stuff. And then we have lecture on Wednesday where I actually explain how this works. So you already know what I'm going to say. Measured numbers, right? Measured numbers are the ones that you produce when you use a ruler or a scale or a graduated cylinder or effectively any other measuring device where the measurement can be subjective. Okay? Does that make sense? So for instance, here we measure the length of that wooden stick. Right? How many centimeters this wooden stick has for sure? But hold on. For sure, it has 4. Now this is their degree in uncertainty. Yes? What do you think? 0.5? Okay. Remember, this is uncertain. Okay? Awesome. So, can't emphasize it enough. You have to estimate the last digit. Okay? And this is why the smaller the marks, the more precise your measurement is. Okay? Hypothetically, can you produce a ruler? Okay. Here's the deal. Can you imagine football field? Like American football, right? It has markings for yards. Right? I mean, nobody does this, but when, let's say, the ball is between, that's the ball, between 2 markings. Let's say it's a 20 and 19, and the end zone is here. And we're talking about the attack, right? So, technically speaking, we can say that's, 19 for sure, and maybe, a little bit more. So, when the ref says, like, 3 more yards to go, maybe 3, maybe 3.5, maybe 3.4, they don't do it. But that's an example of a ruler where markings are yards. You see what I'm saying? Sure, we don't need that much of a precision in this case. So, We already figured out 4.5. Any questions about the process of measurement that we do here? We just don't want to repeat ourselves over and over again. All good? Everybody understands how we got to 4.5? This is sure. This is estimate. Right? Good? Okay. Now, we have a better ruler. How many centimeters for sure? How many millimeters for sure? And then this position. Sure. So the first number, guaranteed? Yep. The second number, guaranteed? And the last one? No. So, we probably, can we go further? I mean, we can. We won't be able to see it with the naked eye, but technically we can. Okay? So, this is a very good example because I found some of you did not realize that we must report zeros sometimes. Okay? So, is 3 for sure? Yeah. And then you say that that's it. It does not stick beyond 3, right? So 3 is sure, and that last 0 is uncertainty. Why? Because maybe if I look at this image, I say, I think it's 2, that's for sure. And I think it's 9. That subjectivity is totally normal. The measurement using a ruler or graduated cylinder is subjective. Okay? So, red line, tell me. Okay, 9. We have further markings, right? So how many further markings? Okay, 2. And then more than that? There's no trick, I'm asking you. There's no trick. Is there more?
1.
You think this? Fine. Or, so basically, out of this, based on the ruler that we are given, which of these 3 numbers, which way is correct way? Yes. The book says it's 9.20. You say it's 9.21. It's fine with me. It's not about the actual length, it's about how you record your measurement. Significant. Go ahead.
So should it always be 3 numbers?
No. No. Okay. That's a good question. So let's give another example, okay? I'm going to change the numbers if you don't mind. 18, 19, 20. Okay? So that's 19, not 9. Do we have 19 centimeters for sure? Do we have 2 millimeters for sure? And let's say it's 2 millimeters and that's it. We're at 0. Does that make sense? All depends on the size of the object, pretty much.
So it could be 9.2.
Can it be?
Okay.
No. You're asking me, can it be number 1?
Yeah.
It can if we use a ruler in which these black dots are non-existent. When we cannot, you see what I'm saying? When we cannot, we don't, the terminal precision is centimeters. So we can only say, I guarantee it's 9, but then that part, I have no idea. I estimated at 2. Remember, the last digit in the number is always uncertain. Okay? Awesome. Sig figs. A bit nightmarish. Really isn't. Okay? So, several rules. Rule number 1. All non-zeros are significant. No matter where, if it's not a 0, it is a significant figure. Okay? So this example shows you 4 different numbers. All these numbers do not have zeros. So, for instance, this number has 5 significant figures. Okay? Now, zeros between non-zero digits. The term for them sometimes trapped zeros. So, if you look at the numbers provided in the table, these 2 zeros in the center, they're both trapped. So they count as significant figures. This 0 is trapped. Now, in the third example, only 1 0 is trapped. We're going to talk about why those don't matter. Okay? And in this number, 2 zeros that are trapped between 4 and 5, and then 5 and 5 are also significant. Does that make sense? I want to emphasize that much less than biology, chemistry almost never has exceptions. Like if we define a trapped 0 as a 0 between 2 non-zero numbers, that's it. That's a definition. There are no exceptions. That's what a trapped 0 is. And it's always significant. There's no situation in which it isn't. I would slightly rephrase this statement to give you better logic about it. Hear me out. So zeros at the end of a decimal number. Trailing zeros after decimal point. Does that make sense? So, let me use this table to show what I mean. So first number, 2 milliliters, right? We have 2 zeros to the right of the decimal point. Everybody agrees with me? They are significant automatically. Number 2, is it significant or not? Yeah, because it's not a 0. So 2 is significant. Those 2 zeros are significant as well. It means that this number, this measurement, has 3 significant figures. Sounds good? Next one. These zeros are significant. This 4 is significant, which makes the 0 that I didn't highlight trapped, which means it's also significant. Therefore, 4 significant figures. Now, those of you who wonder, why the heck are we talking about this? Number of significant figures shows you the precision of your measurement. Does that make sense? For example, if I write down that the volume that I measured is, 2.0, it means that whatever graduated cylinder I used is much less precise than graduated cylinder used for that measurement. Does it make sense to you? Okay? It's all significant figures, shows us the precision of our measurement. So zeros at the beginning. Sometimes called leading zeros. This, and this are leading zeros. Does it make sense? Leading zeros are not significant ever, in principle. Okay? Now, trailing zeros, and I have a bit of an argument with examples here. Well, actually, no, I don't have an argument. Trailing zeros before decimal, not before, but without decimal point. They are considered to be placeholders. They are not significant. So, in this number, these 3 zeros are not significant. This 0 isn't significant. And these zeros aren't significant. Okay? Does that make sense? Yes? Now, the explanation to this lies in the scientific notation. So let me explain. Can we rewrite the numbers in this table in scientific notation? Can we? I mean, we can. Can we move decimal point? Can we? Yes? So let's write the first number in the scientific notation. Where should we move decimal point? How many spots? 1. 4.40. When we switch from that way of writing to scientific notation, the number of significant figures does not change. So 4.40 multiplied by 10 in the power of -1. Okay, let's do the second one. In which direction? To the right. So we have 2.2 power of -2. And for this one, we have 3 by the power of -3. Everybody agrees with these conclusions? Now you can see that each transformation did not change the number of significant figures. It just removes those placeholder zeros. We can do the same trick with these numbers. Can we write it in scientific notation? 4.4 multiplied by 10 in the power of 4. We move 4 steps, right? 8.1, 10 in the power of 2. 6.15, 10 10 to the power of 6. So I'm going to put it as a note. The number of significant figures. Scientific notation does not change the number of significant figures. Okay, so for instance here, 490 multiplied by 10 to the power of 3. All these zeros are significant. All these are significant. All these are significant. The explanation, remember when we write scientific notation, we have one digit before the decimal point. And it must not be 0. It must be between 1 and 9. And everything after 0 is significant. Now, let's talk about this example. So you see 500 and then there is a decimal point. See that? It makes these two zeros trapped. So if I write just this, how many significant figures are in this number? Just this, just 500. 1. But if I add decimal point at the end, 3. Does that make sense? So, when we convert, it's just another example, when we convert from the regular writing to scientific notation, the number of significant figures does not change. Okay, see that? So, this number, for example, has only one significant figure, which is 4. So, this is the way we write it down. That's 4. Okay? That's your one significant figure. All good? You will have questions on significant figures focused mostly on the numbers, like how many significant figures are in this, or which of the following numbers is like 4, 5, 6, whatever significant figures. So you should be able to determine that. So let's do this. We're going to highlight non-significant with yellow. Well, actually, let's do opposite. We're going to highlight significant figures with yellow. So in the very first one, how many significant figures we have? Where do they start? In B, how many significant figures? In a C, how many significant figures? 4. Okay? Well, good? Because remember, trailing zeros at the end are not significant. Okay. We're going to go for another 15 minutes and then we'll take a break because I'm really concerned about the space on the computer. It's kind of a bit of a pain in the butt. Anyway, so my favorite part about metric system, prefixes. How many inches are in 1 foot?
12.
How many feet are in 1 yard?
3.
3, just 3. How many feet are in mile? 5,280 or 60. Does that all make sense? Really? Really? Imagine that tomorrow I will tell you, okay, you're going to have 4 cents in a nickel, 13 cents in a dime, 32 cents in a quarter, and 127 cents in a dollar. That would be a pain in the ass to, use in daily operations, right? Make sense? And yet, imperial system doesn't really help. And we'll show you when we take a break a couple of great SNL videos about that if you're not familiar with it. In metric system, though, everything is based on the factor of 10. Okay, so you can say, okay, you take 1,000 meters, use the prefix kilo, and there you go, have 1 kilometer. Okay? Nobody in their right mind ever uses kiloliter, seriously, because 1,000 liters is equivalent to 1 cubic meter. That's it. Kilogram, though, is pretty common. Prefixes can be, I call them multiplying. They increase the size, or can be dividing. So, kilo, 1,000 of something. I'm going to use something that you're all familiar with, the file size or the memory size on the devices. So the unit of memory is byte. 1 kilobyte, 1,000. If you tell me it's not 1,000, I know. It's 1,024, but let's forget about 24 for now. It's 1,000, okay? Megabyte, that's 1 million bytes. Okay? Gigabyte, it's 1 billion bytes. Terabyte, it's 1 trillion bytes. Does that make sense to everybody? In chemistry, maximum, I think we use kilo at most. And quite frankly, with the units that humans use for measurement, we don't go beyond kilos unless we measure the power of a nuclear explosion. Then we use like kilotons, megatons, so on. We use a lot of units that decrease the size. Okay? So we use 1/10. That's deci. Okay? Are you familiar with the English word, the verb decimate? Sometimes, journalists trying to sound very, very dramatic say that the population was decimated. Decimation means killing every 10th person. So not really, like decreasing population by 10%. It's not really decimation. Centi, 1/100th. Milli, 1,000th. You may notice that in this case, your sort of, factor is 10. When we go milli, we do not have any term for 1/10,000th or 100,000th. We go 1,000th, 1,000,000th, micro, 1,000,000,000th, nano, and 1,000,000,000th, that is pico. The exponents are shown here, and some relationships are demonstrated. So deciliter, that's a unit that is used sometimes. Centimeter, everybody's familiar with that. Millisecond, microgram. By the way, I want to to avoid confusion, do you see that letter? This one? So it's Greek letter mu. Okay? When you write, let's say, microgram, you can write on microgram, or sometimes you write just U. Okay? And then we have nanometer here and picosecond. So, let's fill in the blanks. 1,000 meters is equivalent to
1 meter.
1,000 meters cannot be equivalent to 1 meter. So what prefix should I use to replace 1,000? Does that make sense? I mean, we don't write kilo, then kilometer. Now this is a decreasing prefix. Do you follow? By how much we decrease a gram? Million times, right? 10 in the power of -6, it means it's 1,000,000 times less than a gram. Do you follow? What prefix do we use for 1,000,000 times, but this time less? Micro. Okay? So it's going to be 1 microgram, but they had a note that in medicine, in order to avoid misreading of a letter mu, they always write this, micro. What is the decreasing prefix for 1/10 of a liter? 1 deciliter. Sounds good? So, keeping that in mind, we can derive certain equalities which will lead us eventually to the concept of conversion factors. So inequalities, like 1 centimeter, centi means 1/100th, right? So 1 centimeter is 1/100th portion of a meter. Before we move on, do you agree with that statement? Everybody? What is the official name for a penny? Like, how do we call a penny properly? 1 cent. Why is it cent? How many pennies are in a dollar? There you go. A penny is 1/100th of a dollar. Therefore, 1 cent. Okay? There are similar coins and used to be in other countries. For instance, 1/100th of a franc in France was a centime. 1/100th centime. Now, same story, and based on this, you can see how we can derive that equality using the same logic as 1 cent is 1/100th of a dollar, which means 100 cents is a dollar, right? 1 millimeter, 1 millimeter is 1/1000th of a meter, which means 1 meter contains 1,000 millimeters. Okay? And based on these ratios, you can quickly figure out that 1 centimeter is 10 millimeters. Okay? Now, you can even use decimeter, it's totally fine, which is 1/10th of a meter. Okay, so we can say that 1 decimeter is 1/10th of a meter. Therefore, 1 meter is equivalent to 10 decimeters. Questions so far? We're doing right? Okay, how about that? We're going to take a break first because the volume explanation will take us some time. Okay?